For centuries, humanity has pondered the fundamental nature of existence. What is reality? Are we alone in the cosmos? And perhaps most intriguingly, are there other versions of ourselves, living out different lives in parallel universes? These questions, once confined to the realms of philosophy and science fiction, are now being explored at the cutting edge of scientific discovery, particularly through the astonishing advancements in quantum computing. At its core, quantum computing represents a radical departure from classical computing. Traditional computers store information as bits, which can exist in one of two states, 0 or 1. Quantum computers, however, utilize quantum bits or qubits. Qubits leverage two peculiar phenomena of quantum mechanics: superposition and entanglement. Superposition allows a qubit to exist in a combination of both 0 and 1 simultaneously. Imagine a spinning coin. Before it lands, it's neither heads nor tails, but a probabilistic combination of both. A qubit in superposition is similar, holding multiple possibilities at once. This inherent parallelism is what gives quantum computers their immense processing power. Instead of processing information sequentially, like classical computers, quantum computers can explore many possibilities concurrently. Entanglement is an even more mind-boggling quantum phenomenon. When two or more qubits become entangled, they become intrinsically linked, regardless of the physical distance separating them. The state of one entangled qubit instantaneously influences the state of the others. This means that measuring one entangled qubit immediately reveals information about its entangled partners, even if they are light years apart. This interconnectedness allows quantum computers to perform complex calculations and solve problems that would be impossible for classical machines. These quantum properties enable quantum computers to tackle specific types of problems with unprecedented efficiency. Areas such as drug discovery, materials science, financial modeling, and cryptography are expected to be revolutionized by quantum computing, as these fields often involve complex systems with an enormous number of variables that classical computers struggle to simulate or cannot simulate. The concept of the multiverse, the idea that our universe is just one of many, has captivated scientists and philosophers for decades. While there are several theoretical frameworks for the multiverse, one that resonates particularly with quantum mechanics is the many worlds interpretation, MWI. Proposed by Hugh Everett III in 1957, MWI offers a radical solution to the perplexing problem of quantum measurement. In classical physics, observations are straightforward. If you measure a ball's position, it has a definite position. However, in the quantum realm, particles exist in a superposition of states until they are measured. The act of measurement seems to collapse this superposition into a single definite state. MWI challenges this notion of collapse. Instead, it posits that every time a quantum measurement is made, the universe splits or branches into multiple parallel universes, each representing a different possible outcome of that measurement. For example, if a quantum particle has a 50% chance of being in state A and a 50% chance of being in state B, according to MWI, when we measure it, the universe doesn't just choose one state. Instead, the universe branches into two parallel universes. In one, the particle is found in state A, and in the other, it's found in state B. In each of these new universes, there's a version of us observing that particular outcome. This implies an unfathomable number of parallel realities constantly being created, each representing a different path that events could have taken. MWI is a deterministic theory, meaning that all possible outcomes of a quantum event are realized in some universe. It removes the need for a mysterious collapse mechanism and instead suggests a constantly expanding cosmic landscape of parallel realities. While highly counterintuitive, MWI is a consistent interpretation of quantum mechanics and has gained significant traction among some physicists, particularly as quantum phenomena become more accessible through advanced technologies.
What are the rules of quantum physics telling us? They're telling us that multiple universes could be popping in and out of existence, and we are just one of them.
Gotcha.
Each one with a slightly different law of physics.
Okay.
So there's no limit on how many of these universes there could be. Let's say there's infinite.
Okay.
If there's an infinite, that means there's every possible combination of all particles there ever were.
Right.
In a landmark achievement that sent ripples through the scientific community, Google announced in 2019 that its quantum computer, Sycamore, had achieved quantum supremacy. This meant that Sycamore performed a computational task that would be practically impossible for even the most powerful classical supercomputers to complete within a reasonable time frame. Specifically, Sycamore completed a calculation in 200 seconds that Google Google estimated would take the world's fastest supercomputer approximately 10,000 years. This demonstration marked a significant milestone, proving that quantum computers could indeed outperform classical computers on certain tasks. While the technical achievement of quantum supremacy was monumental, what truly ignited public and scientific imagination was a theoretical interpretation that emerged from this breakthrough. The theory, as discussed, suggests that when the quantum computer performs its calculations, it's not just one sycamore chip working in our universe. Instead, an unknown number of sycamore chips in other parallel universes are simultaneously performing their own calculations. These parallel computations, through some unknown quantum mechanism, are theorized to share data or results, effectively allowing the collective multiverse of sycamores to arrive at a solution far more rapidly than a single chip in a single universe could. This would explain the seemingly impossible speed, as the computational burden is distributed across countless realities. This idea, while speculative, gained traction because the performance of the quantum computer was so far beyond classical expectations that it prompted scientists to consider radical explanations. The notion that the chip, later referred to as Willow in some discussions, might be communicating with other universes, or that its calculations are inherently leveraging the existence of these parallel realities, is a profound and humbling thought. It suggests that the very fabric of reality, as described by quantum mechanics, might be more interconnected and expansive than our everyday experience suggests. While this remains a theoretical interpretation and not a proven fact, it underscores the profound implications of quantum computing and its potential to challenge our understanding of the universe. The convergence of quantum computing and the multiverse theory presents a captivating frontier in scientific exploration. While the idea of parallel universes remains a subject of intense debate and ongoing research, the remarkable capabilities of quantum computers, as demonstrated by Google's quantum supremacy experiment, push the boundaries of our understanding of reality. Whether quantum computers are indeed tapping into the fabric of a branching multiverse or simply revealing the profound and counterintuitive nature of quantum mechanics within our own universe, one thing is clear. These advancements are forcing us to reconsider fundamental questions about existence, information, and the very nature of reality itself. As quantum technology continues to evolve, it promises not only to revolutionize computation, but also to deepen our philosophical and scientific inquiries into the mysteries of the cosmos.